In this video, we're going to talk about a chemical reaction that is used to combine multiple functional groups in order to produce novel functional groups, and that type of chemical reaction is what we call a dehydration synthesis reaction. Now, as a biology major myself, this is the name that I actually prefer because it has a very descriptive way of showing what actually takes place during the reaction. However, chemistry majors normally prefer to use the name condensation reaction, although in the context of this reaction, dehydration synthesis and condensation are viewed as being synonymous terms. So what exactly happens during a dehydration synthesis reaction, and how do we recognize that a dehydration synthesis reaction has occurred? Well, we can simply look at the meaning of the name itself. So whenever we see an English word with the prefix de, for example, to destroy, or more subtly, to deconstruct, that usually means that we are breaking down or removing something. And from the hydra prefix that we see in dehydration, it probably means that we're going to be removing water. So this is actually the first stage of recognizing a dehydration synthesis reaction, is recognizing when one molecule loses a hydrogen and the other molecule loses an OH. Together that results in a net loss of water. So if we take a look at these two alcohol compounds here, we can see that both of these have an OH group, and I've arbitrarily decided that this is the alcohol that's going to lose the H, and this one is going to lose the OH, and then collaboratively they have lost water, and this is the dehydration component of dehydration synthesis. Next, we consider what synthesis means in chemistry, where if you think all the way back to Science 10 and identifying types of reactions, a synthesis reaction is where we have two smaller compounds, A and B, that join together in order to make a larger compound, AB. So we can consider the alcohol on the left to be our A molecule and the alcohol on the right to be our B molecule, and these two are ultimately going to join together. So why does this happen? Well, when the dehydration has finished, remember that it is impossible to create or destroy electrons, which means that the electrons in this bond are still there and need somewhere to go, which means that this bond is actually going to reform by having this oxygen connect to this carbon here that is now missing the OH group on this side. And if we are to redraw what this molecule looks like without the water that has now been removed, and with the synthesis of A and B, here we have the half of the molecule that used to be the A side, and then on the other half we have the molecule that used to be, or the half of the molecule rather, that used to be the B molecule here. And we can see that this is now our AB molecule, because these two molecules that used to be separate are now joined together via this oxygen here. And this linkage, which is also a new functional group because it changes the chemical properties of the hydrocarbon form of this molecule, this is what we call an ether linkage or an ether functional group. Now, biology students will be familiar with ether linkages even if they have never heard the term ether before, because we can see one right here in these two sugar molecules that are being held together in the same way. So an ether linkage is quite important because your body uses ether linkages in order to store extra sugar that it isn't using immediately for the purpose of generating energy. Now, we can also see dehydration synthesis reactions occurring if one of the molecules only has an alcohol functional group. We can see that in our B molecule here, and we can see that our A molecule actually has a carboxyl group here. So again, we begin with our dehydration part of our reaction. Here is the H, and then the OH on the carboxyl is what is removed, and there is our water molecule, signifying that this is the dehydration that occurs. Next, we need to join A and B together, and remember that it's impossible to destroy electrons, which means that these electrons that used to be in the bond to the hydrogen here need to reconnect somewhere, and they're actually going to reconnect to this carbon that used to be the carbon of the acid functional group in the A molecule here. And we can see if we draw our AB molecule, here's the A side that used to be the carboxylic acid molecule, and then joined to this oxygen here that used to be on the alcohol side, and we can see here that this is our AB molecule. Now the linkage, even though it looks superficially similar to that of an ether in that there are two carbons joined by a connecting oxygen here, we see that because of this double bond O, the A side used to be from an acid rather than from an alcohol, and thus this functional group or this linkage is different, and this is what we call an ester linkage. Again, this will probably be familiar to biology students because biology students will recognize esters in large fat molecules like this. Technically, this is what we call a triglyceride molecule, and we can see that each of the individual fatty acids is joined to an alcohol molecule here called glycerol, and we can see the ester linkage right here, here, and here. So ester's quite important in terms of your body being able to synthesize triglycerides in order to be able to store fat for the purpose of insulation and long-term energy storage. Now, the final functional group will also be familiar to biology students, and for the first time, we actually see that the nitrogen-based functional group, an amine, is now involved here. So when an amine undergoes a reaction with a carboxylic acid, we get yet a different type of dehydration synthesis here. So we can remove a hydrogen from the amine because it's impossible to remove an OH because there is no oxygen in an amine functional group, and then we remove the OH from the carboxylic acid here, and there is our dehydration component of the dehydration synthesis, and then we take the electrons that now are missing from the hydrogen here and simply reconnect them with the carbon in the carboxylic acid here. And if we draw our AB molecule, we can see in this case that it's not oxygen, but instead is nitrogen, is the linking atom between the two halves of the functional group that we're making. Remember that amines actually have two hydrogens on them, or at least primary amines do. So remember to draw this hydrogen in here, and then we can draw the rest of the molecule that used to be our acid side. And if we look at what this molecule used to be, we can clearly see that the left side of this molecule used to be the amine and the right side of this molecule used to be the acid, and combined, this linkage joining the two together is what we call an amide bond, although biology students will recognize this as being what we call a peptide bond because this type of linkage is used to hold proteins together. So if we look at a small fragment of protein here, we can see that there are amide linkages every few atoms within the chain. So we can see there's an amide linkage here. Here's the side that used to be the amine, and here's the side that used to be an acid. And then there's another one here, and here, and so on. So for those lacking a biology background, amides are most commonly found as the linkages between these two types of compounds here. And we can see that on one side of this, we have an amine functional group, and on the other side, we have an acid functional group, which is why this type of molecule is called an amino acid, and these are the building blocks in order for your body to make protein. And we can see when we remove water as per the dehydration part of our reaction, and the synthesis part leads us to the formation of an amide bond that we see here. In the next 3 videos in these series, we're going to take a look at a more detailed view of the naming system of ethers, esters, and amides, as well as doing a little bit of practice of recognizing how to see whether a molecule was formed by a dehydration synthesis reaction.